Okay. Recording is on now. Let me share my screen first. Okay, so if you look at my, our syllabus, you see our syllabus is contains grading is one first midterm, second and final, 3 exams, total 3 exams. So we can schedule for a first midterm as actually we need total two midterms, first and second. So we can actually go for first midterm first week of March. I think that should be good. In first week March, I'll give you the letter. It could be Tuesday or Thursday. We'll decide later whose day, but make sure that it should be the first week. First week at March. Okay, on March first week. Okay, so any questions? And exam will be all multiple and true false. This type of question, short question, multiple and true false. This kind of stuff will be in the exam. As it is to the 30%, so at least 30 question will be there. And the course cover, the lecture cover, this exam will cover till our next Tuesday meeting, till 21. That's we cover. That will be in the exam syllabus, first midterm exam syllabus. And for preparation, let's see, you can do for preparation. I believe that you can go for module, and if you follow my lecture, then it is fine. And also you can go for the PDF file, the PowerPoint that I upload, that I have uploaded already. Yeah? Module 1 to PowerPoint and additional PowerPoint, both PowerPoints. But for preparation, I think this is good. Also, if you follow my lecture, that should be perfect. Especially module and the additional things that I uploaded. This is very important. All the summary is in here. So that will be the it will help to take your preparations. Okay. Any question regarding exam and preparation? I'll send an announcement as well today that sometimes beginning of first week of March we're going to be work for our first midterm. Okay. If you do not have any questions, then we can move forward for our today's lecture. So what's we covered so far? In our last meeting, we just learned what is how actually paging works and how CPU executes a process by using the paging techniques. By using paging techniques, and you know that paging is one of the non-contiguous memory allocations. It is not a contiguous memory allocation. The page can be a page can be actually allocated in different locations in computers. Physical address or memory. It can actually you can allocate or your OS can allocate a page from a process in different locations, or wherever actually it finds the space for a particular page. But there are some algorithms. There is some algorithm for page frame allocation as the page allocation. So we'll explore next subsequent classes. Today, okay, let's little bit recap about our paging technique that actually we learned last classes. I'll give you a little bit summary that how page actually paging technique works. So in paging techniques in general, this is your CPU, and CPU maintain one thing. Also, you know that each process contains a page table. Let's say this is for page table process 1, page table of P1 process 1. Page table process 1. What page table does? Page table contains the same number of entry that your process contains. Actually, if your process has total contains total five pages, so here is total in page table also contain total 1, 2, 3, 4, 5, total 5 entries. What it does contains? It contains the page table page frame address. Here is called contains the frame address. Frame address means the RAM. RAM also divided into some frame. Same as the page size, you know, page size. This frame address. Here is, let's say this is P0, page 0. This is P1, P2, P3, P4. Total 5 pages. And here it contains the frame location for process P0. If we start from this is for frame location 0 number frame. This is 1 number, 2, 3, 4, 5, 6, 7. Let's say 8, 9, and so on. This is for RAM. This is your RAM. This is your process. When it creates inside your hard disk drive, this is process. A process actually it contains total 5 pages. So here is total page table contains also total 5 entries. So if this page P0, this is page for P0, this is P1, P2, P3. If it is 5, then 1 is required. 1 is, let's say, P5, P4, total 5 pages. So let's say P0 is situated in here. This is for P0, page location P0. This is for P1. This is for P2, P3, and this is for P4. If it is like this, so in here it's content the frame number. Here is P0 frame number 1. P1 is frame number 3. Frame number 3. P2 is in frame number 5. And P3 is frame number 6. And P4 is frame number, page P4 located at frame number 8. So this is the page table, actually page table entries. It contains the frame location for a particular page, where actually P0 is loaded inside the physical memory. So how CPU translate this execute this process, page process? So CPU, it has also a register called the page table based register. Page table register contains also this that things also located somehow loaded inside your RAM, inside your memory. Of course, the page table. This is the physical location for this page table. It is 9. So 9 is loaded in here, and from here, then CPU asks for the page number, generates the logical address to asking for a byte. It contains 2 things. One is generate the logical address for executions. It contains 2 parts. One is the page number. Another is offset. offset. So if it is page number, let's say 4, and it asking for, if it is page number 4, then what it does, also this is the physical locations, 9 physical address location for page table. So what it does, it will make the summation of page number as well as the make the sum of this page number and this base address. So page number and base address, so it will actually hit this number for page 0, 1, 2, 3, 4, 4 number page. It is actually hit this 4 number page, and by using this offset value, it's get the exact from it. Actually here it gets this exact bit or word that actually CPU requested for. And from here, one step what it does, from here actually it gets the page from this page location or page from this page table entry, it also gets the frame locations for this particular page. For this particular page P4, where it gets this frame location. So what it does in here, it just replace this same thing. It is just here, it will what it does to make this physical address, what it does here, it contains, it just replace this page number by using this frame number. Here 4 will be replaced by 8, and offset is same, always same. So S4 page P4 is located at 8 number frames. So from here it will find this exact location for this physical location for this particular page, and by using this offset, CPU will execute. CPU actually faces this particular byte or word. This is two-step is very important. How CPU convert this logical address to physical address. It is nothing but when it CPU asks for, CPU always generates the logical address. It never asks for this physical address because it doesn't know this where a particular page is located inside the computer's memory. Inside the computer's memory. That's why the CPU always asks for this logical address. I want the 31 number byte or 32 number bytes or 32 numbers word or 64 number words. It generates this type of address, and from this address you can divide into two parts. One is the page number, another is offset. Offset is nothing but actually which byte actually a CPU currently asking for. And then by using this page number and also the page table base address, you can get the page locations. Page table locations for a particular page, where actually CPU asking for. And from this page number, CPU will CPU will get the exact page locations from this frame number entry, from this frame entry. From frame entry, it gets the location for this page, and then it's replaced this page number by using this frame number, and offset is same. And now it is the physical address. Now it is physical address. It is physical address, and from this physical address, it just CPU can ask for this particular byte from these specific locations. Okay, CPU can execute and fetch this byte from these locations, and this is the actually steps that CPU follows to execute a process using paging techniques. Okay. So now let's see. Do you have any question or comments for paging and how actually we can CPU can get the logical address to physical address? It uses a page table. It uses page table to convert the logical address to physical address. Okay. If you have no questions, so let's move forward. So today we'll see some actually some concept. Let's say first, so far what we know that we have this page table. If this is a page table, when you create a process, it generates a page table against every process, not only single page table. If you open 3 or 4 software or programs, it will create the 3 or 4 page table as well. Then each page table, we know that each page table contains the page number sorry, against the page number, it contains frame number. It contains the frame number, physical location of this page, frame number. But apart from this, a page table entries can contain some others information. Let's see that what is others information. Of course, the frame number is frame number. It is the mandatory field. Actually, it's refers to where the physical locations for this particular page. So this is mandatory field. This is mandatory field, and some other field is optional field that can paste table contents. That can actually paste table contents. One is present or absent bit. Present or absent bit. I draw here P or present or absent bit. Present or absent bit, and another is called protection bits. Protection bit. This can be actually more than one bit. That's why protection is called the protection bits. Another is called the reference bit. Reference bit. And that is could be the modified or dirty bits. Okay, dirty bits. So what actually means the? Let's explain what is the reference bit. What is the reference bit? So when CPU actually execute a process, actually it executes a process from a page. When we use the paging techniques, execute a page from page. Also, you know that a process may have many pages. A process may have many pages. From these pages, let's say CPU recently used these pages. So at first CPU use page number, that one CPU for execution purpose, CPU use the page P0, and then P1, then let's say P4, P3, P3 it's used. So what is the recently used by this CPU? If the CPU recently used this page P3, so CPU refers this page recently. So so the entry for this reference bit for a particular for this particular page, the reference bit will be the 1. Means that this page actually CPU refers recently, and other page will be the other page is before this page, before this P3, CPU refers the page P0 and P1. So this page reference bit will be the 0. So reference bit actually maintains the which page is most recently accessed by the CPU. By the CPU. This is the reference bit. And next, let's say the present or absent bit. Present or absent bit. What does it means? The present or the absent bits. Today, in next, we'll actually talk about something called the virtual memory. In there, you also know that you will be know that when you execute a process, a process may have more than many pages. It can be 100 or 100, 200, many pages, or let's say 300 pages or 50 pages, 5, 10 pages, any arbitrary pages. So at a given time, the CPU actually doesn't require to load all the pages for a particular processor. It doesn't require to load all the pages for a particular page. If a process needs total 100 pages, so the CPU or your OS actually doesn't require to load all of these pages inside the inside the memory. From there, it's loaded a few of pages from this 100 pages and executes. When a new page needed, then actually it's just load these new pages from your hard disk or hard drive. So if a page is if a page is currently available inside the RAM, then present bit is 1. If it is not available, the page table maintain this here. Let's say this is 5P5 is not currently available inside the RAM, then this present absent bit will be 0. Let's say P6 is uh, currently inside the memory or RAM, then your P6 will be the 1. Your P6 will be the 1. Present absent means that this page is already inside your inside the memory or RAM. So this is the present or absent bits refers, and next is the dirty bits. Dirty bits or modified bits. Okay, this is very important concept. So let's say currently you are open a process MS Word document. You are open a process called the MS Word document program, MS Word file. This is also a process, and it also divided into some pages, and then you modified these pages. Also, let's say you write some word or some sentence inside this page. Yeah, so everything, that everything is will be loaded your RAM before execution. So in this page, in this page you just you write some sentences. Then what does it then actually modified bit will be set. If you write or if you modify the page, then the modified bit or dirty bit will be set means it will be the 1. If you doesn't modify any pages, then it will be the 0. So how it is important? In our next class we will see that something called the page replacement algorithms. So if modified bit is 0, means that inside the RAM, the page actually you didn't modify anything. So this copy is available also hard drive as well. Your hard drive is available, same copy is available because you didn't modify this page. So when a new page is needed to load actually inside this RAM and replace this page, you need to replace this page. That time you just copy and paste it over there. If it is not modified. But if it is modified, what you need to do? You need to write back to your disk, and then you can replace this page. So this is how it is very important, modified and dirty bits. And next is the protection bits. This actually indicates that whether your page is read only or write only or read and write only, execute this kind of protection. When it is read only, so you cannot edit. When read only is set, you cannot edit. When read and write only, you can edit as well as the read of a particular page. This modified and this protection bit actually means that is stuff. Whether this page is read only, write only, or read or write only. This kind of stuff actually refers these protection bits. Okay. Any questions so far? Okay. Let's be clear. Drawing things before. Okay. I think our next topic is what is the virtual memory. Virtual memory. I already mentioned that. Let's say you currently open 3 processes. This is process number 1. Let's say its contains total 50 pages. 0, 1, 2 till 50 pages. And another process you open, it contains also, let's say, total 10 pages. Total 10 pages. And another process you open, this process also contains total 30 pages, let's say 30 pages. Also your RAMs total, in your RAM total frame, let's say total 50 frames inside your RAM. Till total 50 frames. Total 50 frames. So if you consider, you first you upload this process P1, then you open this process P2, then you open this process P3. So if you use, if you think that when you open this process, so this process contains the total 50 pages. As you know that that the process page size and the frame size is same. So if you loaded all of these pages inside the RAM, then your RAM will be the full. RAM will be the full. There will be no space. There will be no space, and you cannot actually go for this. Those in that case, your process P2 and P3 needs to be wait until actually P3 finished. P3 finish is finish its executions. Huh? So what is virtual memory tells that you at a given time you don't require to upload all of the pages inside the memory. Only few pages you can you can load it inside the memory. The your OS, of course, your OS will be loaded some pages inside the memory, and these pages will gradually actually replace these pages by using others pages. Means that at a given time, let's say your process needs to execute execution for these 3 pages. So 3 pages, these 3 pages will be there, and later also your OS needs the page number, let's say 30 number page. Then what it does, it will replace a one page from here, and then load it these 30 pages and the 30 number pages, and continue the executions. Sorry. So you don't need to upload this whole total pages inside the memory. Yeah? You don't require to allocates the total pages inside the memory. Only few pages is enough to execution process, and always maintain these few pages from your process to your computer's memory. And this type of memory allocation actually known as the virtual memory. Only part of your process at a time inside the memory, not whole process. Only part of this process at a time will be inside the memory. This is known as the virtual memory. Let's say, what is the advantages of virtual memory? There are one thing is that it will increase the degree of multi-programming. You know this, what is the degree of multi-programming? At a given time, how many processes can reside inside the memory? This is called the degree of multi-programming. Let's say in here, if your OS loaded all of these 50 pages inside the memory, if when you open the process P1, then here is only one process P1, and it allocates whole of the whole memory in whole memory. Yeah? It's occupied the whole memories. Only one process inside the memory. So here, what is the degree of multi-programming? Degree of multi-programming 1, because only one program inside the memory. But if you use the virtual memory techniques, then you loaded only few pages. Let's say you upload the total 5 pages from this process, and total 3 pages from this process. Also this process, total 3 pages, and total 2 pages from this process, 2 pages from this process. So if you upload this part of part of programs at a time instead the whole programs, then you definitely your degree of multi-programming will be increased. If you use the virtual memory technique, you can increase the degree of multi-programming. And another concept is that this is very important concept. By using the virtual memory concept, you can execute a process that is larger than your RAM size, your computer memory size. So how it's possible? If you use the virtual memory techniques, let's say your RAM contains total 50 frames and your process contains total 51 frames. 51 pages. So in that case, if you do not use the virtual memory, you never execute this kind of process. You never execute this kind of process because your RAM contains only the 50 frames. Also, frame is equal to page size, so 50 frames. But your process, it contains total 51 frames. 51 pages. So you definitely never execute this kind of process. If you need to allocate the whole process inside the memory. So if you use the virtual memory virtual memory concept, you just upload the half of this process, 5 or 10 process from here, and after execution these 10 pages, then you just replace these pages some other page, and then replace the pages some other pages. This is how you can actually run a process which is larger than your RAM size. Okay. Okay, this is one of the advantages of virtual memory. You can run a process that is larger than your RAM size. Now there is two other concepts. Is that one is called the page hit and page fault. Page hit, page fault. So if you if you actually completed another computer operating system, we may know about this one is called page hit and page fault. Let's recap again that what is the page hit and page fault. Page hit means that this is your CPU, so this is your RAM, and this is also RAM contains some pages from a process, and then your CPU will ask for a byte that actually contains in this page. That's content in this page. So page is available inside the RAM. Let's say your process contains total 10 pages. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 10 pages. And from this 10 pages, you just your operating system uploaded at a time total 3 pages. Total 3 pages uploaded. And then CPU asks for this data that is available in this page. So in this page is available. So it is fine. That means the page hit. The data that actually CPU try to execute that is available inside the memory. But sometimes CPU asks for this data, which contains the page number, let's say 4, but it is not currently. This page is currently not available inside the RAM. So CPU asks for this data, but it is not currently inside the RAM. This is called the page fault. Okay, when page fault happens, then CPU what's actually operating system does. Operating systems will upload the page, let's say page number 4, one of the frame, and actually of course it takes little bit more time if the data is available inside the RAM, like in here. When page hits, it takes less time to execute. And it is page fault, then operating system actually needs to upload the page from your disk to memory. So it takes little more time rather than compared to if the data is available inside the RAM. Okay. So this is two major concepts of page hit and page fault. Okay. Let's see. We are actually talking about this concept because next we'll talk about the frame allocation, page replacement algorithms and frame allocations algorithms. We need to actually know about this small concept before we study the page replacement and some page frame allocation algorithms. Okay. There's another three concept is that we'll learn the frame allocations. What frame allocations? Another is page replacement. Another is called the thrashing. Sorry. It is for thrashing. What is the page frame allocations? So far, you know, in virtual techniques, we need to allocate. Actually, we never upload a whole process at a time inside the memory. We just allocate only. We just upload only few pages inside the memory, computer memory. So let's say you have total P1, P2, P3, total 3 process. Let's say you allocates for P3 total 3 frames. You allocates 2 frames for process P2 and 2 frames for process P3. So this means that this is your RAM. Inside your RAM, you just allocate total 3 frames for process P1 and then 2 frames for process P2 and then next 2 frames for process P3. This is for P1, this is for P2, this is for P3. From here, you can see that P1 actually never, it cannot use the more than 3 frames at a time. It cannot actually get the more than 3 frames at a time. So it can upload only 3 pages at a time. What about the okay? There are some algorithms for frame allocation, so we'll learn later. So this is actually referred as the frame allocations. So how many frames is allocated for a particular process in a short? This is called the frame allocations. Another concept is the page replacement. Another is the page replacement. This is page replacement. What is the page replacement? Page replacement means that which page will be replaced in case of page fault. What is the page fault? The CPU asks for a bytes, but these bytes or word is not currently available inside the RAM. Means that this is the page fault. In that case, what your OS does? OS will allocates the page where the specific bytes is available. So it needs to replace some existing page that is existing page that is available inside the RAM or memory. So if you allocate the total 3 frames for this memory for this process, let's say this 3 frames you allocate for this process P1, and CPU asks for this byte. Here is, let's say this process contains total 4 pages. This is P0, P1, P2, P3. Asks for byte. Here is currently you uploaded P3, P1 and P2. And now CPU asks for a byte that is available inside the page number 3, but page number 3 is not currently available inside the memory or RAM. But what CPU will do, what your operating system will do? Operating system will replace one of the pages from here, and it will replace this. Let's say it replaces the process page number P0. The page number P0 right back in here if it is modified, or if it is not modified, then it is fine. It just replace in here by P3 because this copy is available inside your disk. But yeah, But if it is modified somehow, if you modified some these pages, in that case, of course, you should write back inside the memory, or sorry, inside your disks. Otherwise, you will lose some data. So this is called page replacement. When you need some additional data, the data that is not currently available inside the RAM, means the page fault, then you need to replace a uh, existing page for a particular process. For a particular process, it means the page replacement. There are several algorithms is available for page replacement. We will learn later. Okay, next is the thrashing. What is mean by thrashing? This is very important concept. Let's say what is mean by thrashing. Yes. What is mean by thrashing? Let's say you now let's say you write a code, high level code. Let's say high level code. You write a code for you okay, you declare two variables, integer a and b, and then you make the summation of this variable a plus b. Also, you assign a variable in here, a equal, let's say 10, and b equal, let's say 20. You assign a variable, and then it is inside a process P1. It is inside a process P1. You just click this program. You just open this program to run it, and then of course this process will divide it into some pages. Let's say it's divided into total 3 pages. Here is integer AB. Here is this page contains the A equal 10, and this process contains B equal, this page contains B equal 20, and here you make this sum equal A plus B. So now what it does, let's say also this process it has total for this process, it has total allocation is total 2 pages for this process. 2 frame is allocated for this process. This is process P1, and it allocated total 2 frames. Total 2 frames. This one and this one. And it first it will take in here, execute, okay, integer b, and then a equal 10, okay, a equal 10 in here, and then it needs to go for b equal 20. So b equal 20, let's say replace by in here, b equal 20, and then it requires to sum this page, then it will replace one of these pages. Let's say it replace that pages, these pages. So what we will do here is sum equal a plus b, but inside your RAM now only b is available. There is no a, so it cannot execute. Let's say it cannot execute. So what is does operating system next replace this b, this page, by using the a page. A page b replaced by this a. Again, this page is replaced here. Now you have this a equal 10 in here, but here is no b. B is again actually backs to your disks, your hard disks, but inside only A is available, B is not in here. So CPU cannot perform the sum operations. So it's always CPU hits the page fault and replace the pages, but CPU cannot execute your programs in these circumstances. So you cannot execute the programs. This is called the thrashing. So always we need to avoid the thrashing situations. Okay. So any questions or comment for this concept? Okay. Let's move forward to some algorithms called the frame allocation algorithms. We already know that what is the how actually we needs to why sorry we actually know that why we needs to frame allocations, because we wants to update, we wants to upload part of our pages uh, inside the memory. Your OS actually needs to allocate the part of your process inside the memory. So before we upload, we need to allocate the number of frame for a particular process. So how we allocate the number of frame for a particular process. There are several algorithms is available for frame allocation methods. Let's explore some frame allocations. Frame allocations methods or algorithms, whatever you can say, methods. There is two. First is we explain that there is two methods. One is equal. One is called the equal allocations, and another is called the process size. One allocation is called the equal allocation, and another allocation is based on the process size. Based on this process size, equal allocation is very simple. So let's say this is the RAM, and it contains total 40 frames. Total 40 frames. Let's say total 60 frames. 1 to total 60 frames. Total 60 frames. And you currently open total 3 processes: P1, P2, and P3. So equal allocation, each process will allocate total 20 frames. Total here is called 20, here is also 20. This is simple as this is very simple, a simple allocations method, which is the equal allocations. Whatever the frames is available, number of frames available, divided by the number of process current process. So you just equally distribute the frame numbers for this particular process. If it is fraction, sometimes you can give the floor of this floor of this number. Okay, so this is equal allocations, and so this is not a good technique. From here you can see this if this process needs only, let's say the process P1 needs only 10 frames, only 10 frames, then 0 to 10 frames, only 10 frames, but you allocate the total 20 frames for this process. So also in the also one thing also it is note that if you assign the 20 frames for a particular process, you cannot allocate this process this unused frame for other processes. Means that it's required 20. It requires total 10 frames. So 10 is currently unused. 10 is currently unused. But let's say in P2 it's required total 30 frames. Total 30. It has total 30 pages. 1 to till 30 pages. So you allocate 20 pages. So 20 pages. So still here 10 page is actually you cannot allocate inside the RAM, but here is 10 is unused, but you cannot allocate this 10 frames for the process P2. It is fixed now. When you allocate, then it is fixed. You cannot change it. This is static allocations method. You cannot change during the runtime. And so in that case, you know that this is the kind of disadvantage. Also, P3 may need only 5 pages, total 5 pages. Then 25. Sorry, then 15 frames will be wasted. Total 15 frames will be wasted. So this is not a good, actually good method for frame allocations. And another technique is that you can use some method, but depends on the process size. You can allocate the allocates the frame. So how it does work? So let's say you have total 60, total again 60 is available, 60 frame is available currently, 1 2 3 till 60 frame is available. Also your total three process, let's say process one size is, let's say MB or byte, MB megabytes. Let's say process 10 MB, and then P2 size is 20 MB, and P3 sizes let's say 10 MB. So how it allocates? It allocates the process size, okay, summation of per process P1 10, and the summation of all of these sizes, process sizes 10 into available frames is 60. So P1 will get, in that case, will get, there is 40 into 60, that is 10, is this 2 3 5, total 15, and P2 will get, it will get how many? Here is P2 is total 20, so size is 20, so 20 plus 10 into 60, 20 40 into 60 to 3, here is 10, so total 30 will be for this process, and also for this process P2. Sorry, I'm mistaken here. No, it's fine. It's fine. And then also P3 will get the same as the P1. It is 15 frames. This is how you allocate. Depending on the process size, you just allocates the number of frames. But you this thing you can only just predict it. You don't know from this process size. We cannot decide this how which frames which pages is currently, or how many pages is required to execute a process. We actually don't know. We cannot actually predict it accurately. We just predict from his by using this by using some technique called this process. Depending on processors, we just predict that okay, 15 frames will allocate it, but we don't know that how many pages, how many actual frames, actual pages, frame or pages is required during the execution process. During the execution process, you can only know this how many at a time, how many processes, how many pages is required to execute for a particular process. Okay, we just predict it. This is also kind of predictions. If it is large process, then we actually allocate the more frames. If it is a small process, then we allocate the less frame. Okay. Okay. So, any questions or comments so far? Okay. So let's. We already talked about the two kinds of frame allocations, which is equal allocations and allocation based on the process size. So both are static. You cannot change it during the runtime. Once you allocate the memory for a particular process, you cannot actually change during the runtime. But another technique is called the dynamic allocations memory. How does it work for dynamic allocations? Let's say we have total 3 processes, P1, P2, and P3. P3, 3 processes, and each process needs actually, here is your frame, here is your RAM. Let's say it allocates total, you allocates, this needs 2 frames, here is need 2 frames, here it needs 5 frames. 5 frames. So end up like this. Also total 7. Also here is, let's say, total 7, then you can understand easily. Here also your RAM contains a total 7 frames. Let's say 1, 2, 3, 4, 5, 6, 0, 1, 2, 3, 4, 5, 6, 7. Total 7. 7. Here is 9. 8. 8. Total 8. 0 to 8. 9. Total 9 frames. So you allocate the let's say total here this I say total this is here it needs total 9. Needs total 9. 9 also one assumption is that for dynamic process one assumption is that priority P3 priority is greater than P2 greater than also P1 as well. Priority P3 process priority is higher than other processes. Let's say currently your P1 is inside the RAM, it takes these 2 frames, or P2 is inside the RAM, it takes also 2 frames allocations. Now process 3 actually trying to execute. This priority is high. So it needs total 9 frames. It needs total 9 frames. So how dynamic allocation will does? It will replace this all pages. All pages. It replaces this all pages that is currently available, and it actually allocates for this process P3. Process P3. Process P3. Yeah, for execution purposes. In runtime, actually, it will execute. Even though you P1 P2 also it's inside the RAM inside the memory, but due to the higher priority it just take all of these frames for execution purposes. Also, if you need a process need any extra frame, let's say for process P3, if you allocate the total 2 frames, but it needs the extra frame, for dynamic allocation. It can actually take. You can also allocate this extra frame for a empty spaces and empty spaces. Okay, during the even though you 2 frames you allocate for this process, but for dynamic purpose, in case of dynamic allocation, if it needs some extra pages, it can allocate inside the empty space, or you can allocate this process. You can allocate these pages some lower priority processes or lower priority processes to continue the execution. This is kind of better. It is kind of better technique, but still it has some problems. It is still some problems for dynamic allocations methods. Okay, let's see what is the problem for dynamic allocations method. One problem is called for dynamic allocation methods. One problem is called the starvation problems. Starvation problems. What is the starvation means? A process can be waited indefinite of time. A process can waited indefinite time. You don't know. A process actually sometimes may need to wait indefinite time. Actually, it doesn't know that when it will get the space to executions. Any priority based process, actually it suffers. It's suffered by the starvation problems. So let's see how it works. Starvation, how it works. Again, let's say you have the total 3 processes, P1, P2, P3, and you are trying to currently you know that P3 takes all of these 9 frames. All of these 9 frames. 0, 1, 2 till 9 frames. All of these 9 frames for execution purpose, because P3 is its priority is higher than P2, is higher than P1. So it takes all of these executions, all of these frames for executions, and then P1, P2, and P1 is currently waited inside your disks for completes their execution. It is now currently inside your disks. Then you again open another process. Let's say P4. You open another process, and your operating system seen that its priority. See that its priority P4 priority also higher than P2 and P1. Also, it needs also total 9 frames, or let's say total 10 frames. So it will cover all of this 10 frame again, and P4 will execute now, currently executes. Still P1 and P2 is waiting for execution. But again, if P5 process comes, its priority also greater than P2, P1. Again, it will execute, and then still P1, P2 is waiting for executions. So sometimes this kind of situation can happen in case of priority-based approach. This is called the starvation problem. The process doesn't know that when it will get the chance to execute. So execution. So it can be waited indefinite time. So a process can wait in indefinite time. Indefinite time. This is actually starvation problems. When you use the priority-based approach, always it is suffered by the starvation problems. Okay. Okay. So our next thing is the page replacement algorithms. So we are currently running out our time. So next class we'll learn the different types of page replacement algorithms. Or different type of page replacement algorithms. Okay. Okay. So let's stop here. Let me stop the recording.